In this fourth section of Chapter 8, 8.4, we're going to look at a new type of function called a rational function. We'll look at what their graphs look like, what makes them, kind of how they're different than functions we've seen already in the past. There are some unique things about rational functions that we're going to need to talk about, vertical and horizontal asymptotes. We'll also talk about the domain and range of these rational functions. So first, what is a rational function? Well, a rational function is one typically of the form f of x equals, we'll go with real general here, n of x divided by d of x. Where d of x is not 0. In other words, it consists of kind of a division of two polynomial functions. Specifically, rational functions have an x in the denominator of a fraction. Okay. That'll be kind of unique and to what we've done in the past, and something that every rational function will have in common is they'll be dividing by an x somewhere. Sometimes it's dividing by an x minus 2 or an x plus 3, but there'll be an x on bottom of that fraction. Sometimes the numerator has an x as well. Sometimes it's just a constant value though. Alright, with every new function, and this rational function is a new function, I like to draw what I call a parent function. It is the most basic rational function that I can give you. It's just simply 1 divided by x. There's nothing else down here. There's no x plus something or times something, and it's just as simple as I can make the numerator. It's just a 1. Okay, but this function will give us an idea of what the general shape of kind of every rational function has, and we'll approach it by kind of the same strategy we do when we encounter new functions. We'll do a table of values. So let's begin. We'll just do how about 2, 1, and 0. So start with those points. When x is 2, we get a y value of half. When x is 1, we get 1 over 1, which is 1. When x is 0, well, what happens there? We have 1 divided by 0. We all should know that we're not allowed to divide by 0. So, in fact, this is undefined. We'll talk more what that means on the graph here in just a moment. What about when x is a half? 1 divided by a half comes out to be 2. Let's show these points on the graph so far. We'll come back and get some more here too. Let's start right here with this value. Wherever our function is undefined, I'm going to indicate that by sketching just kind of like a dotted line at that value. This dotted line, and it's hard to see on this graph because it's right on top of the y-axis. It's got a name. It's called a vertical asymptote. Okay. It acts as, you could think of it acting kind of like as a wall in the function. It's a barrier, kind of an invisible barrier that your function cannot cross through, cannot draw through that barrier. Okay, that's a simple way to think of a vertical asymptote. And they always happen at these undefined spots. Okay, so let's plot some points. So we've got the point 1, 1. We've got the point 2, 1/2. We've got the point 1/2, 2. You see kind of a curve of points showing up there. And I'm not going to keep making the table. We can just kind of talk about what the points would be. If x was, say, 5, you would have 1 over 5, you'd have 1/5. You'd have a point that's even closer to the x-axis. If x was 1/5 right here, you get a reciprocal value of 5. So we can kind of see a curve showing up that is kind of bound between the x-axis and this y-axis where the vertical asymptote is. We get something that looks like this. Okay. It just gets kind of closer and closer to the x-axis as it goes to the right. It gets closer and closer to the y-axis as it goes up. It never actually touches either of those axes. Okay. Let's just modify the table that we've got a little bit over here. It'd be easier because we're kind of running out of room down here. If x was -2, we'd get -half. X was -1, we'd get y of -1. -half for x would give -2 for y. We get essentially the same exact points, but just down into the third quadrant. We're going to get this point, get this one, we're going to get this one, we're going to have, we could fill in some more points out here. X is -4 would make -1/4. X of -1/8 would be a y value of -8. We're going to get the same kind of curve inside on this axis or quadrant. Okay, same thing happens. I got a little bump right here in the graph, but it really just kind of flattens out as it goes to the left, flattens out to the x-axis, never touches it, and same thing here. It's going to keep getting closer to the y-axis, but never actually touch the vertical asymptote or the y-axis. Well, that's kind of the general shape of a rational function. You typically have a couple of curves bounded or separated by this vertical asymptote. There's actually another asymptote right inside of here too that we'll talk about as well. Alright, let's talk about something kind of new to the course that has just shown up with this rational function. A rational function is one that we could describe as a discontinuous function. A discontinuous function, besides saying describing it as one that's not continuous, we could say it's one where maybe let's describe it this way. You cannot draw, I'll say you cannot draw the entire graph without stopping. Okay, you have to stop somewhere and kind of pick up your pencil and restart. Like in the case with that vertical asymptote, you had to draw part of the graph and then you'd stop and pick up and redraw the other part of the graph. That's a discontinuous function. It doesn't continue from beginning to end without stopping. Okay. There are two types of discontinuities that we'll go over in this particular section today. The first ones we've already seen are vertical asymptotes. Okay, they always occur where the denominator, I misspelled that, is 0. And that's where you're always going to find them. The other one, and we'll talk just very briefly about this, are simply holes. You'll find like gaps in the graph. And I'm not going to talk about yet where they are, where we see them, but when we get to an example with one, we'll just kind of talk about it there. But this is the main one. We're going to talk quite a bit about vertical asymptotes. Every single one, or almost, I'll rephrase that, almost every single one of these functions we do today will have a vertical asymptote, maybe even 2 vertical asymptotes. Alright, the directions say graph, and state the domain and range. The first thing that I typically do is, let's just do it down here. I'm going to find the vertical asymptote. And it's pretty easy to do. All you do is take the denominator of your fraction, set it equal to 0, and solve it for x. This graph is going to have a vertical asymptote at x equals 3. So I go to 3 on the x-axis, and I put a vertical asymptote. The second thing that I'm going to do is, let's put 1 there. Second thing I'm going to do is I'm going to make a table of values. And instead of having you actually do the table of values by hand and picking numbers and plugging them in for x and working that all out, I'm going to let you use calculator to do that. And I'll show you how to do that now. So we turn on the calculator. If it's not already there, go to the y equals screen, so you're here. And we're going to type in this function. So it will be, I'm going to use parentheses around the top, 2x, divide by, I'm going to use parentheses around the bottom, like that. Let's move this over. And once we're typed in, instead of hitting graph, let's go to second graph. See the table of values, where we can kind of scroll up and down through this table. Notice the table gives you x values, right? X values, and it gives you the y values that go with those x's. Okay, look right here. It tells me that when x is 3, there's an error. That's the vertical asymptote. The calculator cannot compute a point when x is 3. Okay, but let's look at these points that are to the right of 3. And we've got a table of values. We can plot these points, and we didn't need to do it on paper. So just a little bit faster. It's actually considerably faster. So the first point is at 4, 8. Next point is at 5, 5. And we've got a point at 6, 4. We've got a point at 7, 3.5. Got a point at 8, 3.2. Got a point at 9, 3. 10 is at like 2.8. And you can see how the curve is kind of flattening out a little bit. I'll just kind of follow that curve pattern where it's starting to flatten out. Well, now let's see what happens with these points on the left side of that asymptote. Okay, so there we can see right there at the bottom, there's the error, there's the asymptote. So let's pick up right here. 2 is at negative 4. 1 is at negative 1. 0 is at 0. Negative 1 is at a half. Negative 2 is at negative 0.8. Negative 3 is at negative 1. Let's see if there's another easy one to plot. Negative 9 is at negative 1.5 or 1.5. We can see the same thing. It's kind of flattening out as we go to the left. So let's go ahead and connect those. And there's our rational function. Now we're also asked to state the domain and the range. Let's just do the domain on this one. We're not quite ready to talk about the range, I don't think. The domain. Well, domain is essentially every value on this graph, every point on this graph has an x value except for 1. And that's right here, right where the asymptote is. So I'm going to write my domain negative infinity to 3. Okay, that's this side of the asymptote. And then 3 to infinity. That's this side of the asymptote. Now, as you might have kind of suspecting, the graph is flattening out as it goes to the right, and it's flattening out as it goes to the left. There is a horizontal asymptote in there as well. And what I need to do next is show you how do we find that horizontal asymptote. We have a technique for finding the vertical. How do we find out where that line is? Right there. To find the horizontal asymptotes, you compare the highest power terms in the numerator and denominator of the fraction. So let's just go like this. If the function f of x is equal to n of x divided by d of x, where d of x is not 0. Okay, so we've got a rational function. Denominator can't be 0. We can't divide by 0. We don't like that, so we're just going to throw that stipulation in there. Okay, so let's kind of make a list of possible outcomes. What can happen? 3 things can happen. The power of n of x can be bigger than the power of d of x. Okay. The power of n of x can be less than the power of d of x. That could happen. Or finally, the power of n of x can be equal to the power of d of x. One of those 3 things is going to happen every time. Either the power of x is bigger on top than on bottom, it's smaller on top than on bottom, or the powers of x are equal to each other. Okay, that's all that can happen. So, what does this tell us about the horizontal asymptote then of the particular function you're trying to graph? Well, in the first case, there's no horizontal asymptote. Simple enough. Power of x on top is bigger than power of x on bottom. There's none. Okay, there's none every time. If the power of x on top is smaller than that on bottom, then the line y equals 0 is the horizontal asymptote. Okay, that's just the x-axis. And if the powers of x are the same, then the horizontal asymptote, I'll say, is the ratio of leading coefficients. Okay, that'll make a lot more sense when we kind of do the next problem. If that's not making it's not too clear right now, it'll become clear in the next slide. Okay, the directions on this slide say state the zeros, the asymptotes, the domain and range, and graph. I'm not going to worry about the zeros right now. Let's just begin with the asymptotes. The vertical asymptote. I take the denominator x minus 1 set equal to 0 and solve for x. At x equals 1. So on my graph, at x equals 1, there's my vertical asymptote. I'm going to find my horizontal asymptote. And for that, I look at the highest powered term I see on top and bottom. And here they're both x to the first powers. Okay, powers are the same. That's case 3 of the last slide. So if the powers are the same, the horizontal asymptote line is y equals, I look at the coefficients, 4 and 1. 4 over 1, which is 4. That's where the horizontal asymptote is going to be. So horizontally here at y equals 4. Okay. Now we need a table of values. table of values I'm going to use the calculator to do. Okay, so I'm going to parentheses 4x minus 12 divide by parentheses x minus 1. I'm going to go to my table of values. Let's see, right there is the error message. That's the asymptote at x equals 1. Let's start plotting some points now off of that. So at 2 we're at negative 4. 3 we're at 0. 4 we're at 1 1/3. 5 we're at 2. 6 we're at 2.4. Let's skip out to 9 where we hit 3. And just right inside of these asymptotes, try and connect the dots as best you can. We've got our curve. Now on the other side of the asymptotes, so there was the error message. Right here we start at 0. At 0 we're 12, so we're kind of off the graph up here, so let's just go up. Negative 1 we're at 8. Negative 3 we're at 6. Let's see if I can find another easy one. At negative 7 we're at 5. Just go with these 3 points. And there's that part of the graph. Okay, domain and range. Domain is negative infinity to 1 and 1 to infinity. We always break up the domain at where the vertical asymptote was. The range, well, the range is y values, and that breaks where the horizontal asymptote is. So it's going to be negative infinity to 4, 4 to infinity. That's everything we're asked to find. This next function shows us a graph that actually has 2 vertical asymptotes. Let's begin by finding those. I take my denominator x squared minus 1, set it equal to 0. Solve for x, that's the same as x squared equals 1. So take the square root, we get plus and minus 1. So we've got vertical asymptotes at positive and negative 1. Okay. Next, let's find our horizontal asymptote. For this, we look again at the first terms, or the highest powered terms. We have a first power divided by a second power. So power on top is smaller than the power on bottom, and every time that happens, it's the line y equals 0. So this one has a horizontal that's just right here on top of the x-axis. Okay. Now we're ready to graph. So to do our graph, we're going to go to our calculator to make the table of values. Function is x minus 2, so parentheses x minus 2 divided by parentheses x squared minus 1. I'm going to hit second table so we can get some points to start plotting. Okay, let's look first to the right side of positive 1. So there's the positive 1 error on top. At 0, or 2 we're at 0. At 3 we're at, that's 1/8. So just barely comes up a little bit. Tell you what maybe we should do. I'm looking at all these y values. They're all very, very small values. let's say, oh, I don't know, let's say we count this graph every, let's do the y-axis. By quarters. I don't know if that's going to help too much or not, but let's see if that does. So if this first line is 1/4, then 1/8 would be right there in the middle. We go up to a little higher, we come back down at 4. I believe this graph, I kind of really want to know what happens right here at 1.5. So I'm going to go into my table set, change this over to ask, go back to table, I'm going to type in 1.5. 1.5, we're at negative 0.4. So that'll be about here. So this graph comes up through the horizontal asymptote, comes back down and levels off. Okay, go back to auto on the table. Let's look over here to the left of -1. We're at -1 1/3. So that would be about here if we're scaling by quarters, remember. Negative 0.625 for the next one would be about here. Let's see, this is about -1/4. So 4, 5, 6, that's about here. Let's see if we can get another one. It's just going to get smaller and smaller. So I think over here it just does this. And between the two asymptotes, well, we've had right there at 0, it's at 2. We're counting by quarters. As we're up here. I need to see some more values in between there though, so I'm going to go back to table set, change it over to ask, and I want to know what happens at 1/2. On 1/2 we're at 2. What about -1/2? We're at 3 1/3, so we're off the graph up here, so we know we're coming down. What about 1/4? What about 1.8? I think we've just got kind of like a parabola sort of thing right inside of there. That's not an easy graph to make. If we look at the, instead of hitting the table, just look at the graph and let's see what it looks like. And it does kind of look like we've got the curve here, we've got a little parabola region, and although you can't see it because the numbers were so small, it does come right up above the x-axis and then it kind of flattens out as it goes out to the right. Not your easiest graph to do with two asymptotes. On the homework, I'll make sure that we maybe spread the asymptotes out a little bit so that we can get a few more points to plot between them, a little bit easier to do maybe. Okay, I wanted to give you one example of a graph that doesn't have a vertical asymptote but instead has a hole in the graph. They're recognizable because oftentimes the function itself has a factorable numerator. By factoring the numerator, you can see that the denominator cancels out. So the function is essentially just x plus 3. Okay? This function here is the same as what we started with for every single point except 1. And the point that it's not the same is the point that comes from the denominator of that fraction. If I take the denominator that I canceled out, okay, that right there, x minus 3, set it equal to 0, solve for x, oops, get x equals 3. At 3, there's a hole in the graph. That only happens when the factor cancels out, as it did in this particular problem. So here's what I do. I'm just going to graph x plus 3. Starts at 3 on the y-axis. Has a slope of 1. When I get to 3, here's 3, where the graph would go through 3, I'm just going to put a little hole there. So we look like this. And there's our graph. Doesn't look like the other ones at all. It's not curved at all. It's just a straight line that has a hole somewhere in the middle of it. That's it. And that hole is a discontinuity.